So crystalline solids are solids that have a long-range order to their atoms or molecules. They're not random. There's a distinct pattern in how those molecules or atoms are arranged. Here we have two photographs. This is a snowflake, and I forget which one this is. But you see these beautiful crystals. It reminds me of Superman's place at the North Pole, right, with all these crystals sticking out. The shapes of these crystals, Superman. He's got that thing at the North Pole with all the crystals.
Oh,
Yes.
Yeah. I'm not making this up.
just like confusing shit.
I'm trying to bring in, real stuff here. Oh,
I forgot.
you forgot. Okay. Moving along. So how do we figure out how those atoms are arranged, right? They're too small to see. We use X-Ray Crystallography. And so this uses the idea of diffraction that we learned about earlier. So electromagnetic waves can interact with each other. It's called interference, right? This is review. Constructive interference, where these waves are in phase, causes an increase in the amplitude. Destructive interference, when they are out of phase, causes a reduction in the amplitude. In fact, you can actually completely cancel them out. So we remember that video with the guy in the box on the beach, right? When light passes through two slits that are separated by a distance similar to their wavelength, you get an interference pattern. Well, that works with other types of electromagnetic radiation as well, not just visible light. So the spacing of atoms within crystals is about 100 picometers, which is in the region of X-rays. So the wavelength of X-rays corresponds fairly closely to the distance between particles in a solid. So we can use X-rays instead of visible light and pass them through a crystalline solid, and the atoms and the spaces in between them act as the slits and cause diffraction patterns. Those diffraction patterns can be analyzed, and we could figure out what the spacing of the particles is. So this is a typical setup. You've got an X-ray source. You need a lead screen so that you get a narrow beam, focus it on the crystalline solid, and you get a diffraction pattern. So there's some geometry involved here, which some of you will enjoy and some of you won't. And if you don't like it, just shut your ears. So if we've got two waves in phase, and these will be in phase because they're coming from the same generator. We've got two waves in phase coming, and they hit this solid surface. They're going to bounce off the atoms, and this ray 2 is actually going into the solid, and so it's traveling a longer distance than ray 1. It goes in and it comes back out. And so the difference in the distance is this little bit here labeled A. And geometry tells us that we've got an angle here, and this distance is 2 times that distance. A would be equal to d times the sine of theta. And so the distance there is related to the wavelength. You can stick all of those together and come up with what's known as Bragg's law. So n is an integer, because it could be that these waves are off by 1 wavelength or 2 or 3 or 4, whatever causes them to be in phase again. So some integer times the wavelength is equal to 2 times the distance between the layers, sine of theta. And so we can vary the angle at which the electromagnetic radiation, the X-rays, are hitting the solid. We vary the angle and look for the angle where we get a maximum signal coming out. So you can solve Bragg's law for d, the distance between the layers, and that's going to equal n lambda over 2 times the sine of theta. This is a picture of the result of an early crystallography study. And you can imagine that, looking at that result, it requires a little bit of learning about how to interpret that. X-ray crystallography is extremely useful. It's been used to determine simple atomic lattices. It's been used to look at the structure of proteins, and it was very important in the discovery of the double helix structure of DNA. It's also used for other biologically important molecules. So it's an important tool in looking at the organization of a solid. So we're not going to do a lot with this, but there'll probably be one question on an exam about it. So we need to have a clue. The spacing between layers of molybdenum atoms is 157 picometers. Calculate the angle at which 154 picometer X-rays produce a maximum reflection for n equals 1. Well, we've got n lambda equals 2d sine of theta. And that's Bragg's law. And this is asking us to calculate the angle. So we're trying to calculate theta. So we could rearrange this equation, get sine of theta equals n lambda over 2 times d. And we'll worry about getting rid of the sine till later. So we were given some numbers here, right? We've got 157 picometers, we've got 154 picometers, and we've got 1. Well, 1 is obviously n because it says that, n equals 1. The other things we're looking for here, d, the spacing between the layers of atoms, and lambda, the wavelength. So which of these is the wavelength for those X-rays? (154) 154 picometer X-rays, that's the wavelength. And then this is the spacing between layers, that's d. So we can plug these numbers in and find that the sine of theta is equal to 1 times 154 picometers divided by 2 times d, 157 picometers. And the picometers are going to cancel out. So we don't have to worry about doing any unit conversions. So 154 divided by 2 divided by 157. 0.4904. Oh, what the heck, 506. When you're dealing with logarithms or when you're dealing with sine, cosine, tangent, etc., it's always better to have too many sig figs than not enough. If you round this to 0.5, you could end up with a mess. So how do we get rid of the sine? Inverse sine, right? So if we take the inverse sine, which on your calculator is sine to the minus 1, we take the inverse sine of the sine of theta, that is equal to theta. And then we've got the inverse sine of that number. You want to make sure that your calculator is doing this in degrees and not in radians or the other one that I can't remember right now. There it is. So the inverse sine of that number, 29, 3 sig figs seems good, 29.4. degrees Celsius. No, just degrees. So that's the angle where you get the maximum reflection. Any questions?